Good morning to everybody. I would like first to thank the organizer for inviting me here. I'm the first time of this type of workshop, so that is why my presentation is a bit falling apart. But at least the systems are of interest for everybody. So I will be speaking about pneumatic superconducting states in iron pnictides near optimal hole doping. So this is a different pneumatic state which is usually observed in bulk superconductors. We know that in bulk superconductors we have a pneumatic state is a symmetry breaking from tetragonal to two-dimensional rotational symmetry without breaking the time reversal symmetry. So this kind of symmetry breaking was observed in this kind of superconductors, 1, 2, 2. It is observed first in electronic normal phase, and then lowering the temperature, we enter in superconducting phase, and this superconducting phase, of course, it contains the imprint of symmetry breaking in the normal state. So this is the way how it is manifested the pneumatic state in the superconductor. Here we will speak about another pneumatic states which are not related to electronic pneumatics. So we have absolutely tetragonal symmetry or almost tetragonal symmetry in the normal state. Then we enter in superconducting state. Immediately we see the very strong rotational symmetry breaking. So to prove this, that this is indeed so, there was done a lot of experiments, and these are experimental people who did this work. So this experimental work was done in Leuven in the group of Professor Viktor Mashalkov. Many people are from there, but also there are some other groups involved here. And we are responsible only for the theoretical interpretation of this result. Let me begin with reminding you about the diagram for 1 to 2 superconductors. So we have, so in the center is a barium compound. If you start to dope with potassium, potassium is monovalent, barium is bivalent. So actually what we do, we add holes in iron arsenicum plane. So this becomes hole doped regime. By the contrast, if we replace iron with cobalt, we have the electronic doping. So we know very well that there is the magnetic stripe dome orthorhombicity. So there is symmetry breaking of the tetragonal symmetry. We have orthorhombicity here. In some moment appears the superconductivity. We are interested in hole doped materials, and we will speak about materials which are close to optimal hole doping. Optimal hole doping is obtained at 0.4. X is equal to 0.4 doping, replacing potassium by barium by potassium. We will be in 0.5, somewhere here. So the regions around the dome is surrounded by so-called pneumatic fluctuation domain and pneumatic state domain. So what is pneumatic state? What is the order parameter of pneumatic state? So pneumatic state is some state in which the symmetry is, rotational symmetry is broken. This can be just normal structural phase transition. This can be the orbital fluctuation phase transition, so orbital population for nx and ny. dx, y, dx, dxz, dyz orbitals, they have different population. And this can be a pure spin type. It is called spin-driven easing pneumatic state. So what is this? It's when we calculate the average of mx squared, the square of the magnetization, in x and y. So this corresponds basically to measuring the susceptibility xx and susceptibility yy. So, and it starts to break. So they are different. So this is the order parameter of this spin-driven pneumatic state. So this is a dark region here. It surrounds the dome, the magnetic stripe dome, from the electronic doped part. If you go higher in temperature, we have the domain of pneumatic fluctuations, where this order parameters is 0, nematic order parameter, mx squared minus my squared. But the fluctuation of this order parameter is non-zero, is essential, so we have this pink domain surrounded. If you go down by temperature, of course, we will cross a domain where already mi is different from 0. We have a striped magnetism. And what is important, so we have three mechanisms, at least we know, for symmetry, for nematic state, for tetragonal symmetry breaking. This is this one which is described here, spin driven using nematic state. There is just orbital disproportionation in the population of orbital, different x and y orbitals, and the structural phase transition. So in principle, they are all connected. If they are weakly connected, you can separate experimentally to see what is the driving mechanism. But if they are strongly connected, we cannot separate them. Now, we are speaking about a domain 0,5 doping, which is somewhere here. So here we have no nematic fluctuation, no magnetic stripe, no tetragonal, no orthorhombic structural phase transition. So we have absolutely tetragonal crystal. And we investigate the magnetoresistance and the second critical field in this domain. So the experiment was done on some mesoscopic structure, which was spherical symmetric. Yeah? The sample was a layer of this single crystal layer of this closed optimal doping 0,505. The thickness was 1, 2, 3. There was many samples investigated between 1 and 3 micrometers. The diameter of this disk is about 80 micrometers. So this is the experiment. It shows how they measured the resistance. This is Corbino disk design. So you can measure the resistance, then to obtain resistivity. And this is the problem for I don't know, school problem probably. So this is something like resistance is resistivity multiplied by logarithm of external radius over the internal radius. So we have two circular terminals here. And this way is extracted the resistance. And what it was measured? It was measured the resistivity curve in the domain of say, normal to superconducting transition domain. This is, in the absence of magnetic field, is quite sharp, showing that it is more or less regular material. But applying magnetic field, it becomes larger and larger. So how it was measured? The temperature was raised at 150, then the field was applied in a given direction. Well, the direction we start always from 0. This is A or B axis of the single crystal. And then the temperature is raised till a given temperature which we want to measure. And then the sample was rotated and the magnetoresistance in this way was measured, the resistance in the magnetic field. And this was done for many temperatures in this domain and for different values of field from 0 to 9 Tesla. So this is the experiment. So what was observed? So generally we know that the bulk is tetragonal symmetric, and we expect for our magnetoresistance as function of this angle theta to be at least of, say, C4 symmetry, tetragonal. But what was observed, so this magnetoresistance, is it has a strong C2 component. So this is shown in the say, rho phi diagram, and this is a phi. Yeah, we see 2 maximum. In tetragonal symmetry, we should have 4 maximum. Actually, when we raise the temperature, we come to normal resistance at a given transition temperature. It is perfectly circular. So we have no anisotropy, like we know for the materials in this domain. But if you go down, immediately we see the lowering of the symmetry. And this is something unusual. It is unexpected, at least. So they thought that the experiment was done a bit wrong way, because they did a field-cooled experiment for a given direction of field, and then they rotate the sample, and it could be that there is some metastability. So when you rotate to a new angle, the superconducting state didn't relax properly to this new position. And here there are, by say, circles shown the measurements which was done field-cooled for each direction. So they actually coincide practically, so we don't have this metastability effect.
Sorry, the DC, this doping is, how much is the DC?
Doping is 0.5.
No, but the temperature where you go into the superconducting state. So
it is in this transition domain. It's between, so the TC here, TC is 38, I think, 38.
So they are measuring
between 38 and I think 36, something
so
like this.
Basically, it's not really below in superconducting state.
Just above.
Basically mixed.
This is superconducting state, but it is resistivity region.
Huh?
It is resistivity region.
Which means that it's not fully superconducting.
So it depends what is the mechanism of this resistivity. There are vortices which are moving. That is the reason for superconductivity, but this is not the situation that you have alloy. Parts are superconducting, parts are not superconducting.
How do you know this? It is an alloy.
Not really. It is more or less ordered. This 0.505, it's more or less ordered.
You believe that your potassium is perfectly ordered?
No, it's not perfectly ordered. But what we see, this transition in absence of field is quite sharp. In alloy, we will have a large transition, usually. So this is more or less sharp. Of course, it's not 0.505. It is not, say, periodic. More or less, it's ordered structure. So then what was measured also, this is the second critical field. So second critical field is the field at which the superconductivity disappears. So we apply the field. This is type 2 superconductor. So the superconductivity disappears. It depends on the temperature at which you measure. The lower the temperature, the higher the field. So how it was measured also from these resistivity curves, which are here. There was constructed another curves which are, say, depending for a given temperature, resistivity as function of different fields, applied fields, you obtain something like this. Then experimentally they take 90% of this resistivity, they take the horizontal light and they see for different curves, for different direction, of course. You say 120 degrees, 240 degrees, these are different curves. They obtain for different directions the critical field AC2. And this critical field also follow the same, more or less the same law. So we see the C2 characteristic of this material. So what is the main thing here? So in the bulk, we don't observe this. The bulk is always tetragonal. But these are thin films of 1-2 micrometers, and they were prepared at very high pressure. I don't know why. They say 9 or 3 gigapascal. So it could be that they are somehow having some stresses. This is probably the explanation. Okay. So why this is not falling in the normal paradigm? So in the, say, Ginzburg-Landau functional, if you want to couple some nematic state, one of these which we discussed, with superconducting state, it will be of this type. Because this is C2 symmetry, this product of the order parameter, and phi is also C2 symmetry. And the terms in Ginzburg-Landau should be of tetragonal symmetry, symmetry invariant. So then there are two scenarios. Either we have a normal situation that phi, this nematic order, it nucleates in the normal phase. Then when we come to superconducting phase, this will be giving already some finite value phi, and this is at nucleation we have a second order in order parameter term which will influence the HC2. But this is not the case because we know that in normal phase it is tetragonal symmetric. There is another possibility that due to this term we have a nucleation of the the nematic order parameter and the mixing of this delta S, delta D. But so in the Ginzburg-Landau, we have also term which is proportional to phi square. When you minimize this with respect to phi, you obtain a term proportional to delta S, delta D. This is a usual thing. When we substitute here back, we obtain a term of fourth order. And the nucleation, the term of fourth order doesn't play a role. It is small. You only retain terms of second order. But second order, they are all perfectly symmetric. You have to observe, again, a tetragonal symmetry of your magnetoresistance angular dependence. So this kind of explanation, they are not applying here. So the usual nematic state cannot be the explanation for this experimental data. So if you do a summary, we see that we have very weak anisotropy in normal state. The nematic state is strongly manifest already at the transition to the normal state. So it is something intrinsic to superconducting state. That is why we call it nematic superconducting state. Yeah, again, this is how we go down by temperature, what phases we pass in the case of normal nematic, conventional nematic states, and this is superconducting nematic states. We come immediately to anisotropic superconducting state. Well, to describe these things, we applied the linearized Eilenberger equation, so probably you know these things. So this is how it is described superconductivity in the presence of some magnetic fields and effects and so on. So actually, this is anomalous green function. It depends on this. Okay, probably I will not enter in these details. So what is important here is to use this equation. You need to know the pairing potential, and you need to know the Fermi surface, and you need to know the Fermi velocity on the Fermi surface and all points on the Fermi surface. And then we basically we use this to calculate first. The most simple is the second critical field. So we use to solve this equation to calculate the second critical field. But second critical field, this is a nucleation of superconductivity. So therefore the delta, which is order superconducting parameter, will be small. And because it's small, we can apply some perturbation theory to find F1. Actually, what kind of, this iteration, it's done by iteration. So you take this term. This pi is generalized momentum. So pi is, for instance, is minus IH gradient, say minus E over C, say A. And A is a vector potential of applied field. We can take applied field because this is on the disappearance of superconductivity. We don't have Meissner currents and things like this. So yeah, so this is, you pass this term to the left and then you express phi1 via the terms in the left. It will be this phi1 with this term, but you can take from the previous iteration. So you can do this iteratively, substitute in the equation for the order parameter, for the gap, and you'll obtain an equation which will be linear in the gap, but with increasing powers of these VF pi terms. So it will be a kind of equation which is linear in delta. So if we solve this equation, we obtain the HC2 field as function of temperature. For different temperature, obtain HC2. So this is how it is done. First of all, we need our electronic structure. So it is parameterized by tight binding the LDA calculations. They are known, for instance, for this kind of optimal doping. There was a calculation of this. The parameterization for this was extracted already, and we use it for 0505. So this is how it looks. So we obtain different Fermi surfaces, a bit different. So this is in a rigid band scheme. So what we obtain is this Fermi surface, so we know everything we need from this side. But we also need the pairing potential the pairing potential, and this is the main thing. So this is actually our goal is quite modest. We want only to explain. We will not calculate from first principle this potential, but we only need to represent it somehow with a minimal number of relevant components, and to show when this mixing of components can give you what we observe. So for this, we use this, say, eigenvalue equation for Fi. Say you can decompose this potential like you decompose any function in some set of independent functions. You can decompose this in different components of this type, Fik prime. Yeah. So, and we take, generally it involves an infinity, but we take only the relevant one, and they will enter with this coefficient g. So this coefficient g, this is, say, eigenvalue of such kind of equation. Yeah. But we say that, suppose that we already solved, we know this Fi, and Gi will be our, say, parameters which will vary. So what kind of Fi we should take? So these are the S dx square minus y square and some other components. So what we know about hole-doped 1 to 2 materials? We know that in the limit of extreme hole doping, we have a D wave. So this was established. In another limit, we have an S wave type. And we are somewhere here, and they should cross somehow. This is the energies of these two states. And if they are crossed, we should have here some quasi-degeneracy of these states. So this is the basic thing which we use to explain these experiments. So we will take as our minimal model, we will mix F1, it will be S type, and F2 will be x square minus y square type wave. So this is how they characterized by tetragonal symmetry group. So what we then do, we suppose that we have some internal stresses which are very weak to be observed in a normal phase. In the resistivity in A and B lattice parameters, we don't observe this. They are very weak. But because these two states, say S and D, are quasi-degenerate, even a small mixing term, which will be G12, can have effect on the say, observable magnetoresistance. So we introduce one more G12 coupling parameter here. Now this is how we represent our pairing function. This function f, which are, say, they are known, so how they behave on the surface of Fermi surface of different pockets. This is taken from here. So these are known things. And this is a simulation which we obtain for magnetoresistance. If you take the mixing only S and D, x square minus y square, we obtain this blue line, which is exactly 135. So if you combine this and this, you'll obtain some maximum which going in a perpendicular direction. Well, they are both equivalent. But this still doesn't coincide with experimental observed curve. That is why we admix the third state. If you admix one more state here of this type, then we can reproduce the experimental second critical field. So we can say, if all this is correct, that in this domain, hold-up domain, we have a small domain. Actually, we varied the concentration by 10%. It was from 0.45 to 0.55. We have a domain of so-called nematic superconducting state. Now, how we simulate the magnetoresistance? So why appears the resistance? The resistance appears on this system due to the vortices. This is type 2 superconductors. We have vortices where you apply, you have a field, you apply the current. These vortices, due to Magnus force, they start to move. And moving, they create dissipation. And this is the reason for resistance. And well, there was the basic theory is Anderson-Kim activation creep model, which was proposed a long time ago by Anderson. So it describes the resistance due to the vortex motion via some activation mechanism. It is of this type. And the activation energy is this. Delta G is some internal energy of condensate occupied by this vortex bundle. So which, there are bundles of vortices which jump. This is the model. R0 is the resistivity, normal resistivity at the temperature of transition. And there was another alternative model proposed later by Tinkham, which is basically use the same activation type physics, but it is expressed a little bit different, the resistivity as function of this activation barrier. 5 minutes, okay, I'm finishing. And now, at this delta G, this is the energy of condensate in the region occupied by vortices. So vortices actually, in this domain, the condensate is destroyed. The magnetic field enters. So the energy of condensate, which is destroyed by this, it's you can express via second order critical field if you are close to normal superconducting phase boundary. This is the Abrikosov formula from seminal paper of Abrikosov. You can show that for anisotropic superconductor, it is also valid, at least for single band anisotropic superconductor. So this is how it was simulated with these two the resistivity curve. So they are quite well. So we can simulate the resistivity curve. And then with this model, we simulate the, say, in-plane magnetoresistivity. So this is experimental, and this is the theoretical. So it can reproduce quite well. Qualitatively, at least, it reproduces quite well the change of magnetoresistance. So we got it from this is different temperatures at field 9 Tesla. So at low temperature, the resistivity disappears. At high temperature, you see there is no absolutely oscillation. It is absolutely tetragonal, symmetric in the normal phase. So it's a perfect circle. Okay, now, of course, there is a point of what about we have 6 parameters actually. For if you mix 3 phases, 3 states, we have 6, say, parameters lambda. Gamma, ij, this is a coupling between different symmetries. So you know this statement of Neumann that if you have more than 4 parameters, you basically should not believe the theory. So what we can say? We can say that the parameters, the main requirement is for different fits. They have to be, some of them should be close. In some calculations, maybe they are not very close, but in any way, they should be of comparable strength. So what is the, say, support for this? So the support, there was some Raman spectroscopy this is for optimal doping. And they found that say, subdominant component, x square minus y square, which is higher. And in energy, it has still 0.6 60% of lambda for the dominant component. There was also some simulations in spin fluctuation, say, mechanism, based on spin fluctuation mechanism of these different components, and they obtain as function of J and U. These are the 2 parameters, electronic repulsion parameters and exchange in this system, that they can be obtained for some values G and U, some close values of dominant and some dominant components. So this is a kind of support. Another support, it comes from an earlier work which we did for these systems, not related to nematicity. It was a dependent current in this kind of system. And this is how it looks. So this is a current, you apply a current, and you see when the superconductivity disappears as function of temperature. And it has such a kink. And again, it can be simulated by, say, here it was Ginzburg-Landau simulation. So finally, it is obtained something like a generalization of the Tinkham formula. With basically, you can have 2 parameters, these 2 parameters, and the dependence is like this. So here we don't have coupling between condensates, or it is very weak. So in this case, we, even with zero coupling, which is correspond to our case, we suppose the coupling is very weak, but only for two components, we can simulate this depairing current. So and the corresponding TC for each state separate, they differ by the ratio is around 0.9. So this is in line, for instance, with the TC which you obtain here, for instance. They also the ratio they are called quite close. They can be the TC for different components. So actually I came to the end. So this is the conclusion. So we observed the nematic superconducting state. We call it like this, and in these thin films of 1 to 2 materials that are close to optimal doping. Thank you for your attention.
Thank you for being kind. Questions?
Are there any measurements for the extreme hole dop case? So for instance, potassium iron to arsenic 2 or rubidium or cesium? Because last year there were some measurements not at the superconducting states, at the normal states, but they measure nematic fluctuations there for the extreme hole dop. So nematicity is being observed.
Yes,
even
maybe. In what materials?
And it's a different. It was in the potassium.
What materials? Bulk materials or films?
This was STM experiment. I think it was.
Some films. Yeah, you can't have easily these things.
Well, because
this is what we also suggest here, that when you prepare films, they're on surface or they are prepared under high pressure, you have some internal stresses and they induce very small perturbations which are in a normal phase, they are not observed. Or maybe they observe, like you say, it depends on the extent how much is. And then this is, but the key point here is that they are quasi-degenerate. So this S state and D state, from barium to calcium, they somewhere intersect, and we are just in a region where they probably intersect. This is the main idea. Then small perturbations can produce these effects. Yes?
When you say it is not accompanied by C4 symmetry breaking, was it checked with X-ray scattering?
Yes. Well, it was, that is why this group of experimental people, they did transmission electron micrographs.
Yeah, but X-ray scattering, then you're very sensitive to breaking of C4 symmetry.
Yeah, they don't see difference in A and B.
So they, okay.
No, in this kind of experiments they don't see. They see a little bit in magnetoresistance in a normal phase. By eye you see it's a perfect circle, but if they do measurements they see some...
X-ray scattering is much more sensitive.
Well, so at least within this sensitivity they don't observe. This is what they check. They checked for twinning, they checked for many things, because then we came to these things. Yeah.
Can I simply very naively say that the main idea is that you have, say, superconductivity of S wave, that is positive, plus D wave, plus minus.
Yeah.
If you put them together, then you have, say, plus which are extended,
Yes,
and
exactly.
minus which are
Exactly.
removed. So that
Yes, this is the main idea.
It's
Yeah.
not C4 but C2.
Yeah.
F
It is this. So if you mix only these two, S and D, you obtain exactly 135 degrees, because the lobe is going in this direction.
Because
Yeah,
it's actually plus and plus N,
exactly. But
plus and minus red and red N, and red
Yeah,
and blue
yeah.
substrate. So finally you
yes, it is.
so that's actually the main simple physical picture, right?
Yes, of course. Yeah.
If there are no other questions, let's thank speaker again.